Okay, so let us start. Let me know if you can hear me properly. I'm audible, right? Okay. Okay. Uh, so today we'll be discussing Lorentz transformation mostly, and from next class onwards we will go on to discussing spinors and Dirac equation, because I saw in this particular week, like fifth week, the lectures are only on Lorentz transformation, so maybe we can get onto spinors and Dirac equation from next session onwards. But before we start, again, do you have any questions or comments? Related to what we discussed last time or anything else?
I have a doubt related to the video lecture.
Yeah.
I, I, I'm sharing my screen.
Okay. Okay.
Here it is like index is mu and but here there is rho and sigma.
Oh, I see. That's a typo. Okay, we'll be discussing these things only today. But yeah, that is a typo. It should be mu nu on the right hand side also. So it's j mu nu equal to I x mu del mu minus x nu del mu.
Like I have a doubt. Like if we put this here, like here it will be mu and it will be contracted.
Yes.
So how will we find rho sigma element? Like it will be a scalar.
Okay, so this is corresponding to. Let me mute you because that is causing an echo. Yeah. So, Aman, would you mute yourself?
Yes, I'm muted.
Okay. So, what I was saying, so that is the generator corresponding to Lorentz transformation. Now, now you will have total 6 generators, 3 corresponding to the rotations and 3 corresponding to the boosts. Okay. So this rho and sigma are basically denoting those indices. These are not space-time indices. So we will basically be discussing this particular thing. I think it will get clarified to you. No, yeah. Any other questions, Aman?
No, I don't have any other questions.
Okay. Okay, fine. So before we get on to discussing Lorentz transformation, let us discuss what happens if there is a translation. Oh, sorry, the screen, I need to share it again. Okay. So, suppose you have x coordinate which is getting translated by some fixed amount a. Okay, so let's say there is a function, call it psi,
ஈவெண்ட் நான் போறேன் சண்டே வர முடியாது அப்படின்னா அப்ப வெனஸ்டே வா அப்படின்னாரு. வெனஸ்டே வந்து சார் எனக்கு ஒரு வீக்கா டைம் வேணும்.
So you have a function, let's say psi, which basically measures the value at each location x. Okay, and after this particular transformation, that function gets modified to some other function, call it psi prime. If this particular transformation is a symmetry, then that would imply that the new function that you are getting should be equal to the old function evaluated at the old location x. Okay, so psi prime of x plus a is basically psi of x, and from there you can see what is psi prime of x, that is psi of x minus a if you replace x by x minus a. And you can always Taylor expand this function, and that will give you del psi del x and so on. So this is basically exponential of minus a del x acting on the function psi of x. Okay, now from quantum mechanics you know that the momentum operator is basically minus I del x. I'm taking h cross to be 1. So if you replace this del x on that exponent, you get psi prime of x to be exponential of minus I a momentum acting on psi of x. So this dictates the fact that this momentum operator is basically generating the translation that is started with, and that is a well-known fact to us. We know that the generator corresponding to the translational symmetry is nothing but the momentum, and that's what we have showed here. Are there any questions on this?
Hello, ma'am.
Yeah.
Sorry for interruption. I just came in bed. Can you please give me a small detection of what you are doing right now?
So so since Dirac equation and spinor, these are not yet touched on the lectures, so we plan to start spinors and Dirac equation from next class onwards. Today we will be just confining ourselves to Lorentz transformations. There was one question on Lorentz transformations also before you joined, so we will discuss the Lorentz transformation only, and we will show that how the Lorentz transformation will keep the equation of motion of the Klein-Gordon equation invariant. I mean the equation of motion of the Klein-Gordon Lagrangian, which is nothing but the Klein-Gordon equation, that will remain invariant. And we will also show that the Lagrangian corresponding to the Klein-Gordon field is a Lorentz scalar, which is necessary for the theory to be Lorentz invariant. Because if the Lagrangian is Lorentz invariant, then the equation of motion that you obtain by extremizing your action by varying the field phi, that will also be Lorentz invariant. So these are the things we will discuss today, more or less. Yeah. Okay. So right now we have started with, before going on to Lorentz transformation, we have started with a translation of x coordinate, and then we are showing the corresponding generator which is generating that particular transformation is nothing but the momentum operator, which is well known to us, that if there is a translational symmetry in your problem, then the corresponding conserved charge is the momentum. Okay. Is that good?
Yes, ma'am.
Okay. So this is the corresponding generator. Generating the translation, the translational symmetry. And this is the parameter by the amount by which this translation has been done, the parameter. Okay. Now suppose instead of translation, we are performing a rotation. So you have a vector, call it r, that is becoming r prime. The rotation, the representation corresponding to the rotation group acting on that r vector. Okay, and you know what is the rotation. Let's say you are performing a rotation by an angle delta of theta along z-axis. Okay, so I mean about z-axis you are performing a rotation by an angle delta theta. So you know what is the matrix representation. That's cos theta minus sin theta. Let's say this is a vector in 3 dimension. Okay, and we will go. We'll start discussing it. We'll go on to discuss the 4 vector when we start discussing the Lorentz transformation. So far, let us confine ourselves to 3-dimensional vector. So this is the rotation matrix. If you perform a rotation about z-axis by an angle delta theta. Okay. Now you can, since delta theta, consider delta theta to be an infinitesimal parameter. So you can Taylor expand this cos and sine, and that will give you 1 0 0, the identity, plus delta theta times 0 minus 1 0 1 0 0. So basically this is nothing but the matrix representation of the corresponding generator, which is generating this particular rotation. Okay. But let us see what this generator is. So let's call the transform vector to be r vector plus delta r. Okay. So your initial vector was, let's say, x, y, z, and that has modified to x prime, y prime, z prime, and that is equal to x minus y delta theta, y minus x delta theta, z. Is that clear? This rotation matrix, when acts on the initial vector you started with, that will give you this r prime, which is nothing but this. So what is delta r vector? That is basically y delta theta x hat plus x delta theta y hat, and this can also be written as r delta theta, which was along z hat, cross r vector. Right? Is this clear?
Can you please explain the last step?
Yeah. So I'm saying, so r vector was capital R acting on R, and this I'm writing in matrix notation. R prime is x prime, y prime, z prime, and this R that we have written here, I have substituted in here So that is so this implies x prime, y prime, z prime so this is equal to 1 minus delta theta 0 delta theta 1 0 0 0 1, okay, acting on x y z. So that is basically x minus y delta theta, and so this we wrote as r plus delta r, and here I am writing the delta r vector. So delta r vector is minus y delta theta along x hat plus x delta theta along y hat. Okay. So this is delta theta along z cross r. Is this clear now? Because the last step is, so you have delta theta here and r vector is x, y, z, and that will give you minus y delta theta plus y hat x delta theta, correct? So this is equal to is this clear to you, Dhanush?
Yes, ma'am.
Okay. Now let's say the same thing that we did for translation. So psi prime of r is basically some, let's say some m, which depends on the parameter psi r. This okay, psi of r inverse of r. Okay, so what I'm saying is, suppose this rotation is a symmetry of your system. This rotation about z axis by angle delta theta is a symmetry. What does that mean? After the rotation, let's say you again have a function, call it psi. After the rotation, the modified function evaluated at r prime should be same as that of the original function evaluated at the vector before the rotation. So that is what we mean by symmetry. And so this would imply that psi prime of r is, or psi prime of r vector is psi r inverse acting on that r vector. And if we take r to be that, since we have taken the rotation is happening by an infinitesimal parameter delta theta, we can write this as r minus delta r, because here inverse of r is getting multiplied with that r vector, and you can then Taylor expand gradient of psi. Since it is infinitesimal, we are neglecting the higher order terms. Now we have seen what is the delta r vector, that is delta theta along z hat cross r vector dotted with grad acting on psi. Okay, now we can rewrite that last equation as delta theta z dotted with r cross grad. This is well known operation, and then if you replace so p is minus I grad, p vector is minus I grad, so if we replace that grad by ip, we get psi of r minus delta theta z hat right. So this implies psi prime of r is 1 minus I delta theta r cross p so here, so this was infinitesimal, but we could have done this the finite transformation, and then we could have written this down as exponential of minus I theta r cross p acting on psi, that function. So here this denotes the generator which is generating the transformation, and this is the parameter, corresponding parameter, and you know very well this is nothing but angular momentum. Okay, so since so this will be equal to exponential minus I theta jz where j is r cross p. So the angular momentum along z axis is basically generating this rotation along z about the z axis. So I mean these we know from beforehand. So in this particular language, now we will discuss the Lorentz transformation in four vector notation. So is this clear? So I was a little bit sloppy here. So when I am writing just two terms, I mean this is a infinitesimal translation, or I could have written this as, let's say, x is becoming x plus some delta a. Okay, so x prime is x plus delta a, or this is becoming psi of x minus delta a. Plus the other terms. So this is exponential of minus delta a psi of del x. But in order to get the finite translation, what we can do is so in order to get the finite translation, what we can do is, so by finite translation I mean x is becoming, let's say, x prime, which is x plus a, where a is finite. And that finite translation you can obtain by call a to be n delta a, so that limit n tending to infinity exponential of so psi prime of x is equal to 1 minus delta a. So you are basically performing this infinitesimal translation by n number of times. So that will give you the finite translation. Now you can replace that delta a by a divided by n, and you know very well this limit will give you exponential of minus a del x. Okay, so limit of 1 minus x over n whole to the power n is exponential of x. So and then replace this del x by the momentum operator to get the corresponding generator for finite translation. Likewise, here also we have done the infinitesimal rotation. Okay. So this is the corresponding finite rotation. But in order to get the finite rotation, what we can do is use the same trick that we said earlier for the translation, finite translation. So in order to get the finite translation, you can write down the angle theta to be n times delta theta, and then perform n number of times that infinitesimal rotation, and then take the limit n tending to infinity. And this is nothing but this exponential of j. Okay. Is this clear? Are there any questions?
So ma'am, so the theta is here is a continuous variable and the delta theta is somewhat discrete here, right?
No. Delta theta is still continuous, but it's infinitesimal. Meaning, so the higher order terms are not here. We can truncate the Taylor series in the first order of delta theta only. So higher order terms are not there. So that's the infinitesimal rotation. Just like here we were saying delta A was infinitesimal, so we are neglecting the higher order terms in that Taylor expansion. Okay, and in order to get the finite translation, we are taking a finite parameter A, which is like n times delta A. Delta A is small, but you are defining your finite parameter to be n times that delta A, and then taking n to be infinity, which means you are performing the infinitesimal translation many times in order to get the finite translation. I mean, instead of going over this, we could have just written A here and would have taken the other terms, and that would have also given us exponential minus A del x. But this is another way of saying the same thing. Taking delta A to be infinitesimal and then defining a finite parameter, which is like capital N times delta A, where n is large. and in that limit also you get this same thing, exponential minus a delta x, del x, and that del x you can replace by the momentum operator, because we know this operator, that momentum operator is basically del x, so we can replace it, and this is also known to us that the generator corresponding to translational symmetry is nothing but momentum. So did I answer your question?
Yes, ma'am. So both A and theta are in continuous only.
Yeah, continuous. They can take yeah, not discrete. Okay, so we have discussed translation and rotation so far. Now,
Ma'am, can you please scroll up?
yeah,
Just there, the last page actually.
okay.
Yeah, that's one.
Okay. Now let's get on to Lorentz transformation. So okay, before that also, so we did translation along x. Now suppose we are performing space-time translation, so x mu becoming x mu plus a mu, then what will happen? So just like we obtain, so space-time translation, so just like we obtain psi prime of x to be exponential of minus I a px acting on psi of x, when you did this transformation, x going to x plus a. Now for the space-time translation, the function will get modified as a mu p mu acting on the initial function. So sorry, let me not call it p mu, but some other generator, call it o mu, okay, where O0 is nothing but your Hamiltonian. You know the conserved charge corresponding to time translation is nothing but Hamiltonian. Likewise, O1 will be momentum along x, O2 will be, or let me call it OX, OY. I mean, you understand, right? Here mu goes from 0, 1 to 3. So 0 corresponds to the time translation, 1, 2, 3 corresponds to the spatial translations. So O1 is Px, O2 will be Py, and O3 is Pz. And this we checked explicitly. And right now we just generalized it for space-time translation. Are the corresponding time translational and spatial translation. Generators. Okay. Now let's talk about Lorentz transformation. What is Lorentz transformation? So just like spatial translation, time translation, and rotation, these are also a kind of transformation which takes your coordinates to be lambda mu nu x nu, such that the invariant length, this length x mu remains invariant. So rotation also has that property that r vector square remains invariant. So r prime square remains equal to r square, and that gives you that property that r transpose r is basically identity. Okay. So likewise for Lorentz transformation, this is the constraint that lambda has to satisfy. Let's see what is that constraint at the level of lambda. So x prime mu is basically rho x rho. Then we can replace, so x mu is becoming x prime mu. Okay, and this we can write as g mu x rho okay. Let me know if you have any difficulty in any of the steps. So this x rho I'm replacing by g rho sigma x sigma, where g is the metric which lowers and raises the indices. Okay, same thing I have done on this side, left hand side. This x prime nu I have replaced by g mu nu x prime nu. Okay, and then so x prime mu we can replace here. So this is lambda call it rho x rho g mu nu lambda sigma x sigma. Okay, so comparing both sides, we can see that the constraint satisfied by lambda is this. Okay, is this clear? Okay, now this matrix, just like we saw that R, we could have in the infinitesimal rotation case, R was like identity plus delta theta times a matrix, which was nothing but the generator. Suppose we consider this lambda to be delta mu nu, which is again the identity matrix but 4 by 4, plus generator, call it omega mu nu. And if we replace this in this constraint, then it turns out that omega mu nu plus omega nu nu is equal to 0. Let me try to derive that. So if we replace this here, so delta rho mu plus omega g mu nu times delta sigma nu plus omega sigma nu is equal to g rho sigma and yeah, so this would imply plus omega rho mu g mu nu delta sigma nu plus delta rho mu g mu nu omega sigma nu, and the last term is basically neglected because again we are considering infinitesimal Lorentz transformation. Okay, so this is equal to g rho sigma, but the first term turns out to be g rho sigma, right, because this is non-zero only when mu is same as rho and nu is same as sigma, plus omega rho mu g mu sigma plus g mu sigma, sorry, rho nu omega sigma nu. So these two gets cancelled out and we are left with omega rho sigma plus omega sigma rho is equal to 0, which means omega rho sigma is actually minus omega sigma rho. So therefore the generator corresponding to this implies there are 6 generators. Corresponding to the Lorentz transformations. Why 6? Because the infinitesimal parameter is actually antisymmetric under the exchange of rho and sigma. So it means if you have this 4 by 4 matrix which is antisymmetric, means the diagonal 4 elements are all 0, and antisymmetry would imply the upper 6 elements are basically negative of the lower 6 elements. So basically you have 1, 2, 3, 4, 5 and 6 total. Total 6 parameters corresponding to the 6 generators. Okay, is this clear? Are there any questions? Okay. which implies that omega is antisymmetric. Under the exchange of the two indices. Okay. Okay, having said this, now let us see what are the generators for Lorentz transformation. I mean, we already know that the generators are nothing but 3 rotation and 3 boosts, right? So we basically expect to derive these. So let's consider the most general transformation. So x mu becoming x prime mu, which is lambda mu nu x nu. So what will happen to a field phi x mu is becoming phi prime of x prime mu So we demand this to be a symmetry. So we demand the Lorentz transformation to be a symmetry, which means we need to equate these two things. After the transformation, whatever field configuration you have, that labeled by the new coordinates should be equated to the initial field configuration labeled by the space-time coordinates before the transformation.
Ma'am, just repeat the statement again.
I'm saying that the field configuration that you have obtained after doing the Lorentz transformation and which is evaluated, or basically which is labeled by these coordinates after Lorentz transformation, this entire thing should be equated to the initial field configuration labeled by the initial space-time before the Lorentz transformation. Actually, this is easier to understand this way. Suppose, I mean, this is the argument given in Peskin. Suppose phi, yeah, so phi is a field which is basically giving you a value at corresponding to every location in space. Okay, so you have a space-time configuration. Let's say there is one point x0 where okay, so you have this space-time configuration where there is some distribution, let's say, and that distribution is such that at x0, if you evaluate phi, that is the maximum. Phi of x0 gives you the maximum value. Now, let's say you have performed a transformation on this density distribution that you have. On this distribution that you have performed a particular transformation, lambda. So you now have a different space-time configuration, but the maximum will still occur. But the maximum will now occur where? At lambda x0, and the field has also become modified to phi prime. So phi prime evaluated at delta x0, lambda x0 must be same as, so phi prime lambda x0 is giving you the maximum value now after doing the transformation. So that must be same as phi at x0. So this implies phi prime at x0 is same as phi lambda x0. I mean, this is the claim when this transformation lambda that we have performed is a symmetry of your system, and this must be true for all points in space. So instead of x0 we replace it by x. So phi prime of x is phi, sorry, not lambda here, it's lambda inverse, phi lambda inverse x. So same thing we are saying here. So this means phi prime of lambda mu nu x nu. What I said, is this clear? What I'm trying to say here? For the transformation to be a symmetry, this condition has to be the case. Let me know if this was not clear. Are there any other questions on this? Okay, I'll proceed then. So this implies phi prime of x mu will be phi of lambda inverse x. Okay. Now consider this transformation to be infinitesimal, so that phi prime of x is phi of, we can suppress the indices here, but anyway, phi of x minus call it some lambda inverse mu nu we are taking an infinitesimal transformation. Okay, so instead of calling it lambda, let us call it omega. So it's omega mu nu. So we have taken lambda mu nu to be equal to delta mu nu plus omega mu nu, just what we had taken in order to derive the constraint satisfied by this lambda, and we just derived that omega is basically antisymmetric in mu and nu. So the same thing we are substituting here, because it's lambda inverse, we get a minus sign in between. Okay, so this is phi prime of x. So what is delta of phi? So the change in the field is minus x nu del mu phi. The same change has to happen for the Lagrangian. So we can derive what is the conserved current. conserved current J mu will be equal to del mu phi times delta phi. What is delta phi? Delta phi is minus this change in the Lagrangian. So this we derived earlier, so I'm not going over that derivation. Okay, so before writing that step, this must be equal to the total derivative of omega mu nu x nu. You see why that is the case? That is the case because this is antisymmetric under the exchange of mu and nu coordinates, omega mu nu. So you see, this will actually give two terms here. Let me explain it. So if we take this derivative mu nu x nu, we will get that term that is already there. Sorry. X nu but it will also act on this x mu, right? So from there we will get another term delta mu nu L, but this will give you plus omega mu mu. So but since this is antisymmetric, we know that all the diagonal elements are 0, so that's why this term is 0. So in that for that reason we can write down this particular term as a total derivative of this term inside. So this is equal to omega mu nu x nu del mu L. Okay, so we know that any transformation is a symmetry whenever the Lagrangian changes at most by total derivative. So since here the Lagrangian is changing by total derivative, the transformation that we are considering, x going to x prime, the Lorentz transformation, is basically a symmetry. So that means there are conserved currents and corresponding conserved charges. So conserved current we know is given by this formula which we derived earlier, and right now just using that. So there used to be a minus sign in between, but you see delta L is having a minus here, so that's why this will be plus in between. Now yeah, so this is equal to minus Are there any questions in between? Any step? Any issue? I don't know if I'm going too fast. Okay, so it's cleared, all clear. So this is equal to minus, let's take omega mu nu outside. Del mu phi Okay. So this is equal to omega mu nu sorry, I have used same index more than okay, so see, this is not dummy index, and this mu index is basically coming from this, so we shouldn't use the same mu index for this delta phi term. So delta phi, we should use this mu to be some other index, so that's the issue here. Let's call it rho. Okay, call it rho. And now let's take omega rho nu out. So if we do that, here we have omega mu nu, so there we need a delta let me write another step in between. This is equal to minus del rho del mu phi omega rho nu x nu del rho phi. Let's call it omega rho nu so that we can take it out. And delta mu okay x nu L. So when we take that infinitesimal parameter outside, we are left with delta mu rho x nu L. Rho I should put in the covariant index. Yeah, I hope it's fine now. So this is equal to minus omega rho nu T mu nu T mu rho x nu. You remember this is the energy momentum tensor that we obtained earlier. So T mu rho is nothing but the energy momentum tensor given by del L del mu phi del rho phi minus delta mu rho L. Okay. So okay, now let us use the property that omega is basically antisymmetric under the exchange of mu and nu, but the energy momentum tensor doesn't have any such property, so we can rewrite it as minus, so let's rewrite this omega mu sigma add sigma nu, so that this is the metric tensor which lowers and raises indices, not the delta function, the Kronecker delta, not the Kronecker delta. sigma nu sorry. So this can be rewritten as minus rho, okay. So this implies J mu is equal to minus omega rho nu T mu rho x nu plus, same thing we can rewrite, but let us exchange mu and rho indices. So rho nu x rho, okay, and by 2 because both the terms are same. Now we use the property that the omega nu rho is basically minus omega rho nu. So this implies J mu is minus half omega rho nu T mu rho x nu minus T mu nu x rho, and we call that term inside the bracket to be the corresponding current. X nu T mu
Ma'am,
rho.
that's it.
Yeah,
Can you please explain me 2 steps before?
yeah.
Last 2 steps.
This one and that.
Yeah.
This one? Okay, so what we are doing, so this was J mu, right? The same term I'm writing again here. See, mu rho is getting summed up, nu is also getting summed up. So these are dummy indices. So I'm writing the same term again here, but with nu replaced by rho and rho replaced by nu, okay, and then dividing by half, and then using the property that the property that we have already derived for omega, which is antisymmetry. So here I am replacing omega nu rho by omega rho nu minus omega rho nu, and that is giving us this expression.
Okay, ma'am.
Okay, so now this is the conserved current. So the corresponding conserved charge, you know the charge you can obtain. Okay, now yeah, you know that you can obtain the charge by integrating over all space the zeroth component of the conserved current. So the conserved charges is d3x j0 let's say when rho and nu both are I and j, okay. So ij means these are taking values from 1, 2 and 3. So this is qij, and these, as you already suspect, are nothing but the angular momentum, right? You understand why? Because our transformation was x mu going to lambda mu nu x nu. Now lambda mu nu we considered to be delta mu nu plus omega mu nu. Now this rho and nu, these indices are nothing but the corresponding indices of this omega, rho and nu. Okay, so this is basically rho nu, j mu. So when mu and nu both are I and j, it means you are basically performing rotation along x, y and z. Like in your you're performing rotation. These are not boosts, because boost will have one time coordinate and any of the spatial coordinates, either x, y or z. So when we are taking rho and mu to be ij and finding out the conserved charge, it is nothing but the angular momentum, total angular momentum of the field phi. Okay, so this is the conserved charge, total angular momentum. Now remember in the earlier case, when we just considered rotation, we actually had shown that Jz is the rotation along the z-axis. So now, and it was, what was it? It was r cross p, right? So the same thing we should get here. Let's see. So J0 ij is equal to xi t0 j minus xj t0i. But if you remember, what was t00? What was t00? T00 was Hamiltonian density. T0i was momentum density. Right? When we integrated t0i over all space, we obtain total momentum. So here this is nothing but xi, then momentum density. I don't know how do we define that. Let's call it some pj minus xj pi. So you see, this is like, so when I and j are 1 and 2, it's x1, or call 1 to be x and j to be y, so it is x py minus y px, and that is nothing but jz, right? Because jz is r cross p z component. So if you take r cross p z component, you get xpy minus ypz. Sorry, xpy minus ypx, and that's what we have here. So it was just an illustration of what we have obtained is the most general case, and upon considering I and j to be 1, 2, or so 1, 2 will give you jz. Likewise, if you take 2, 3, that will give you jx, and so on. So okay, and so this was total angular momentum. Now in order to get the charge corresponding to the boosts, you need to consider rho to be 0 and nu to be I. So let's write that down. So Q0I will be equal to J0 0I d3x. This is equal to d3x x0 t0i minus xi t00. Okay, so these are the conserved charges corresponding to boosts, boost along ith direction. Is it Clear? Okay. So now yeah, now the last thing that we promised to do in this session, we will show that the Klein-Gordon Lagrangian. By the way, Aman, you had questions on this, I guess. This J, mu, rho, nu. You were asking why there are so many indices. Now is it clear to you? Here mu denotes the space-time. I mean, this mu is actually telling you the current along which direction. So we know that if we integrate the zeroth component of the current over all space, we get the conserved charges. Now this rho and nu, these are basically telling you are performing the Lorentz transformation along which directions. So if rho, nu both are ij, it means you are performing rotation. And if one is 0 and another is I, it's the boosts. And as we have shown that omega is antisymmetric under the exchange of nu and rho and nu indices, it means there are 6 independent such matrices. So that's why both cannot take 0, 0 value, because the 0, 0th component is actually 0. In the matrix representation of omega, you have 0 in the diagonal, and upper triangular is same as lower triangular up to a minus sign, because it's antisymmetric. So you have 3 rotation generator and 3 boosts.
Just a minute, you said J mu. The mu correspond to what?
This mu also corresponds to space time only. So when we are saying mu equal to 0, I mean mu 0th component, when you integrate, you get the conserved charges. But this mu has nothing to do this mu has nothing to do with the Lorentz transformation you are performing. So the Lorentz transformation directions are not coupled to this particular mu. The Lorentz transformation directions are being encoded by this J mu here, which is contracted with this omega. Lorentz transformation directions are this rho and nu indices, which are being contracted with omega, rho, nu. These are all space-time indices only. Actually this was, if I give you the analogy from what we derived earlier, maybe it will become a bit clearer. So when we did the space-time translation, so here in session 2, so this was the space-time translation. Okay, so phi got modified by xi mu del mu phi, and that was the change in the Lagrangian. And we said that this is the stress energy tensor. Now see here again you have 2 indices, right? One is mu, which is basically this mu, and another is nu, which is contracted with xi nu. Now xi nu, this nu is encoding the direction along which you are performing the translation. So when nu equal to 0, it means you are performing time translation. So that's why, and okay, before we say that, when you integrate the 0th component of the current over all space, you get conserved charge, and that is also explained here. So this is the 0th component of the current here. That 0th component of the current, when we integrate over all space, we get conserved charge, because if we take time derivative, you get J0 dot, and from this equation, if you replace J0 dot by minus gradient J, that gives you 0. So that's why the zeroth component of the current integrated over all space gives you conserved charge. Now that is what we are saying here. So zeroth component of the current is nothing but T0 nu, and this nu is telling you the direction along which you are performing the translation. So when nu is also 0, that means you are finding the conserved charge corresponding to time translation, and that is T00. And this T00 is giving you the energy density or Hamiltonian density. Okay, sorry, here why is it written 4? Sorry, I think there was some confusion that day. Okay, it will not get, anyway, this is not 4, this is actually 3. Yeah, anyway, so the point is, when nu is 0, it's time translation. When nu is I, so here we also showed, so when nu is I, it means these are the conserved charges corresponding to spatial translation along ith direction, and that gives you momentum along I. So the same thing we are saying now, but instead of having just one index, we now have two indices, because we are doing Lorentz transformation. We are having 4x4 matrices and so on, but the logic remains the same. Here rho and nu, these are being contracted with omega, and that's why what I was saying follows. When it is I and j, you are performing rotation in space. When one is 0 and another is I, you are performing boost. Because now, is it clear, Dhanush?
Yes, ma'am. So I have a doubt from that previous session too.
Go on.
Like there is J0, total sum of J0 is conserved.
Del mu J mu, yes.
Like this gives conserved charge, but this J0 is in terms of T, it has component T mu nu. So I'm thinking like momentum individually, like whole sum is conserved, but like momentum is individually, and these are also conserved. Like this total charge is J0. So J0, when expressed in terms of T mu nu, have two components, like 0, one is conserved when sum over. So like all the momentum energy overall should be, sum should be conserved, or they are individually conserved.
So the current J mu. So I couldn't understand your question completely, but let me still try to say. So this del mu J mu equal to 0, that gives you that J mu is conserved. So this is conserved current, but in order to get the charge, you need to integrate the zeroth component of the current over all space. So T00 denotes the density, and when you integrate it over all space, you get the conserved charge, which is the energy. And you know the energy is the conserved charge corresponding to time translation. Did I answer your question? Likewise T0I is the conserved current, which we can also call to be the momentum density. When you integrate it over all space, you get the total momentum.
Like charge would define only for scalar, like J is also conserved, no? That I was amazed.
J is conserved current, yes.
Yes, okay, I understood.
Yeah, J is conserved current, and that we are calling. Yeah, I mean, this is what I was explaining, that if you take time derivative of this charge, it becomes 0, so you call Q to be the corresponding charge. Actually, this charge we are saying because J in electromagnetism, you write it as rho, comma J vector, 3 vector J, sorry, J mu. So since you are basically integrating, if your forward current turns out to be, if you are in electromagnetism, let's say, then the forward current turns out to be rho, comma J vector. So you are basically integrating that charge density, so that's why this is called charge in general. Anyway, if that was a confusion. Okay, let me proceed. Are there other questions, Aman?
No.
Okay, so now we will show that the Klein-Gordon. Okay, so what have we learned so far? We have learned the Klein-Gordon Lagrangian. We quantized the corresponding field. We quantized the Klein-Gordon field, and we also derived the equation of motion, which is the KG Klein-Gordon equation. Yeah.
Just before getting to next topic, can you please summarize the topic that we so far learned in this class? Just a bit. Just summarize it.
Yeah, more or less that is what I was doing.
Because first we just went through translation and then rotation, then we just jump into Lorentz transformation. So, what I like to learn is what is the connection? Why just we jump from here to there, like that?
So Lorentz transformation. Okay, why we jump to Lorentz transformation is because we are in quantum field theory. We want Lorentz transformation because we are now incorporating special relativity with quantum mechanics. So that's quantum field theory, and you know that Lorentz invariance is a property of special relativity. So we have learned Lorentz transformation because we want our quantum field theory to be invariant under Lorentz transformation.
Oh, okay, ma'am.
Yes. So but Lorentz transformation is not just rotations in space, like it's not just rotation along x, along y, along z, but you know Lorentz transformations are, so if you are performing a boost along x, then your x prime becomes gamma. Let's say you are performing boost along x, then your t prime becomes gamma ct minus vx over c squared, call ct to be x0, so its x0 prime is gamma x0 minus beta x, and x1 prime becomes gamma x1 minus beta x0. So that is the rotation, sorry, that is the so the matrix, and x2 prime will be just x2, x3 prime will be x3. So when you are performing boost along x1, okay, so the corresponding matrix will be lambda 0 1 gamma minus beta gamma 0 0 minus beta gamma gamma 0 0 0 0 1 0. Okay, so this is what you do in special relativity, right? You can perform boosts along x or along y or along z, and in general we want our quantum field theory to be invariant under Lorentz transformation, which also has those rotations. So before getting into Lorentz transformation, which requires us to deal with these 4 vector notations and so on, we just did a warm up on translation and rotations in general, and we showed how a particular function will change under the rotation and translation, how we get the generators, and the same generator we now have obtained but using the 4 vector notation for Lorentz transformation, because we will use Lorentz transformation to ensure that our quantum field theory, whatever system we are dealing with, are invariant under Lorentz transformation, because that is the requirement for special relativity. Is the motivation clear now? Why we did this?
Yes. Yeah, yes. But at last, we just came to the conclusion of total angular momentum, right? That's confusing me. Why we just came to arrive at total angular momentum is conserved, not conserved. We just came to that part. Why?
No, it is conserved. So it is the conserved charge. We called it total angular momentum because just the way we called this to be the total energy or the Hamiltonian, which is like T00, and this was the 0th component of the current corresponding to time translation. So just because we are integrating over all space, we are calling it total angular momentum. You can think of it to be the angular momentum density. Just like T00 was the energy density in quantum field theory.
Okay.
Okay. Now, so let's see how the Klein-Gordon Lagrangian will get modified if we perform this Lorentz transformation. Okay, if we perform the Lorentz transformation and want that to be Lorentz transformation to be a symmetry of our system. So the Klein-Gordon Lagrangian was of del mu phi minus m square phi square, right? So phi, so under Lorentz transformation, x prime mu will be lambda mu nu x nu, or the field phi prime of x, phi of lambda inverse x. So let's see how the mass term is getting modified under the Lorentz transformation. So mass term is half, sorry, there is a plus. This will become half m square phi prime of phi prime x whole square, which is equal to half of m square phi square labeled by lambda inverse x. Okay, so it's invariant under Lorentz transformation. But now let's look at how the del mu phi, the derivative of the field phi, is getting modified. So del mu phi will become so this is del x mu acting on phi. Okay, now remember x mu is becoming lambda mu nu x mu. So we after the Lorentz transformation, this will become phi prime x. So this is nothing but del mu phi of lambda inverse x. Now let y to be lambda inverse x. Okay, so that means del x mu will be del y nu if we write down all the indices. Y nu is lambda inverse nu mu x mu, so we can take the derivative, sorry, del nu. So therefore del mu phi becomes lambda inverse nu del nu acting on phi labeled by lambda inverse x. Okay, so therefore that kinetic piece of the Klein-Gordon Lagrangian under the Lorentz transformation will become del mu phi prime let me write another step in between. So it will become del mu phi prime evaluated at x del mu phi prime. Okay, so we are making the indices covariant just to be able to replace these two by what we have obtained. So this is equal to lambda inverse mu, let me use a different rho mu del rho phi okay, then lambda inverse sigma nu del sigma phi. Okay, now we have derived the property of satisfied by this lambda. So lambda inverse rho mu g mu nu lambda inverse sigma nu is nothing but g rho sigma. Okay, so therefore del mu phi square becomes, so we can write these lambda matrices and the matrix tensor del rho phi till sigma phi. So these are not product, okay? Just like we write phi at x. Now we are just trying to imply that this derivative is also not with respect to x but with respect to lambda inverse x. So that's why we are writing the entire thing labeled by lambda inverse x. Okay, so don't get confused. So this is equal to g rho sigma del rho phi del sigma phi. So this is basically del rho phi whole square, the argument being lambda inverse x. So therefore the Klein-Gordon Lagrangian has become half of del rho phi square plus m square phi square, the whole thing labeled by lambda inverse x. But you see the form of the Lagrangian remains the same as before. So it shows that the Klein-Gordon Lagrangian is a Lorentz scalar. Therefore since the Lagrangian is Lorentz scalar and you get the action by integrating this Lagrangian over d4x, Lagrangian density over d4x, so the equation of motion that you obtain by extremizing your action also remain Lorentz invariant, and that is required because we are incorporating special relativity, and Lorentz transformation is the property that must be satisfied by a special relativistic theory. Okay, so we can stop here. Let me know if you have any questions. Last time I took this live session on Sunday, and after that there were no announcement on NPTEL portal, right? Like whether the session will be on Friday or Sunday.
A mail came on my email that it will be on Friday.
Okay, let's see. Fine. So, okay, so let's meet next week then. Are there any questions?
I have that first question I asked. I have still doubt on that.
Yeah. Which
question? Present, one video I was showing.
Yeah. Now show me the video now.
It is showing?
No. Can you share your screen? You haven't started sharing yet. Yeah.
Now it is showing?
Yes.
But
yeah. I'm not able to see anything yet. Yeah.
1 minute, my laptop is slow.
No problem.
This was here J-mun is contracted, so it is scalar.
Wait. I can't see yet.
The screen is not showing.
No, I can see some other screen. Just wait. I think it will come. Maybe there is some delay.
I will present once again. I think some I presented another window.
Okay.
This
Yes.
now it is showing
Yes. Yes.
like here it is like both indices are contracted. So I think like it is scalar.
Okay. So just a second.
I should mute.
No. 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 It's. Oh, okay. I will mute you. Don't worry. Yeah. You go back to that. So. Yeah. There is echo. Let me mute you. Yeah. So here omega mu nu. Okay. So here it is. So we have used a different notation, the but the point is same. So here rho and sigma, these are denoting the directions along which you are performing the transformation. So if rho is, let's say, 0, then you are performing, no wait, something else is here, just a moment. Yeah, so mu nu is getting contracted with j mu nu. Yes, that's correct. And j mu nu are the rotation generators. So there are 6 rotation generators corresponding to 0, 1, 0, 1, 0, 2, 0, 3, and then 1, 2, 1, 3, and 2, 3. So so this is also clear from this context. So he has derived in a different way, not going over that method. We just used integration over the 0th component of the conserved current. But this is what we were writing. Remember when we were doing the rotation, we wrote. Let me. Just a moment. When we did the rotation, we wrote psi prime of r to be 1 minus I delta theta jz. Remember? So he is using that same notation here. So delta theta and jz we got because we took theta to be along z direction, meaning we took rotation to happen about the z axis, and that gave us jz. And what is jz? Jz is nothing but j12. So you can see there was that contraction, but the language used here and the language we used to derive the conserved current and conserved charges for the Lorentz transformation are a bit different. But here it's scalar, yeah, absolutely. Omega mu nu is getting contracted with j mu nu.
Like I have no doubt. Like I think it is like matrix. It is used to only summation like matrix. I think
Yeah.
because but if it is scalar, then this will not make any meaning like this.
No. So that rho. So see, in the left hand side you have x prime rho. So suppose rho is 0. So then it is showing that what is happening to the 0th component of your x vector. Okay, 0th component of x vector is basically equal to that matrix whatever you have, lambda 0 sigma x sigma. So sigma is being summed up. So x prime 0 is equal to lambda 0 1 x1. Okay, let's start with lambda 0 0. So x prime 0 is lambda 0 0 x0 plus lambda 0 1 x1 plus lambda 0 2 x2 plus lambda 0 3 x3. That's what it means. Okay.
Like this scalar is like matrix. Like this scalar on contraction will not give a number but a matrix.
See, so you can write the matrix notation as well. So what you can do is, on the left hand side you can write a 4 by 1 column vector, the entries of which will be x prime 0, x prime 1, x prime 2, x prime 3, and that 4 vector is equal to this matrix lambda rho sigma, which is a 4 by 4 matrix, which is being acted on another 4 by 1 column matrix whose entries will be x0, x1, x2, x3. You can think of in both these ways.
But like I am not able to understand like this. This is like if we like matrices and tensor notation is mixed here. I think like this is a scalar, but how the scalar we can take this component, but it is contracted, so it does not have any like like this components. But here it is written like it has components. Like both the terms should have like identity will have the components like two. But if this is scalar, then it will not have these two components. Like if we evaluate this, if we get a number, then it will have only one component. But we have to take how we'll find this two components, which we have to multiply like so.
So I think a better notation would be identity. So identity with rho in the contravariant index, sigma in the covariant, multiplying x sigma minus half omega mu nu, then j mu nu whole, only j mu nu is having that rho sigma index. That can be a better notation. But did you understand what we did?
I understand. I have to see this video again. Like I will see that calculation part. But I was thinking that how I will do this exercise. Then I will put here like. But here
see the
both are up index.
Yeah. So see the whatever is written in this j mu nu, that should also not have rho and sigma indices. It should be mu nu. So yeah, as I was saying, so this j mu nu will have another two indices, rho and sigma. Then only the right hand side will make sense, I think. But I haven't watched the lecture. Maybe you can look at Piskin. Probably some kind of a notation is there. This kind of a notation is there.
Okay, I will see. I will ask later. Like, but like if you put here like this, but it has only upper indices. But here it has up down.
Don't think that entire thing. So, listen. So as I was saying, this left, there is a third bracket, right, on the right hand side. So put that third bracket only with j mu nu. Okay, and correspondingly the identity will be x rho. Instead of identity you have x rho minus half omega mu nu. Okay, so let me write it down for you. So x prime rho was written as identity minus, what was it? I. Was there any I? I forgot. Can you remind me? Omega mu nu, j mu nu.
In the video lecture it was I minus I by 2 omega mu nu.
Okay.
Lower index and j mu nu upper index.
This is what is written there, right? And you are getting confused. So
yes.
So instead of writing it this way, think of it omega mu nu Okay, J mu nu. Now you don't have any confusion, any other confusion. So J mu nu rho sigma is basically x rho del sigma minus x sigma del rho. And I think there mu nu, so when it is so omega, let's say 1 2 will mean this is J1 2 and that should be Jz. Okay, so I think there is some issue with the notation. It should probably be rho sigma I have to see. I have to see. I have to check the lecture and then probably I'll be able to tell you. I mean, what he is using. But okay, but the same thing we also did. But they're the indices we. Yeah. So here the indices we kept very explicitly so that everything is clear. Like this rho nu here is getting contracted with this rho nu here, and these two indices mean the directions along which you are performing your Lorentz transformation, and this mu denotes this mu index on the left hand side. So that's why when we so basically so J0 mu nu is basically x mu T0 nu minus x nu T0 mu, and that is nothing but x0 p nu minus x nu p mu. This is what was written there also. I mean the lecture that you were showing me, but there the indices were a bit confusing, but you can think of in this language. The same thing.
I will think, then if I have problem I will ask in next video.
Okay, fine. Oh, there is a live session you were saying?
Like next week I will watch this, like I will try to understand your notation and compare with what sir has told, then I will analyze, and if I have problem then I will ask next time.
Sure.
Like which book to follow for this special relativity part?
I mean, I'm basically following the book by Peskin and the lecture note by David Dom. So you can, there are many books on quantum field theory actually. So
Like where I can study this Lorentz group, like this.
it's there in the book by Peskin as well as David Dom's lecture note. You can also look at I think the book by Ramon. Maybe there also you will get a good discussion. Okay. So let us stop here.
Thank you.
Yeah.
Thank you, ma'am.